السلام عليكم، أهلا وسهلا جميعا. تسمعون الصوت؟ واضح، جميل. حياكم الله جميعا. Hello Mr. محمد عبد الباري. How are you? Are you doing good? Sorry, you're muted, I guess. If you can unmute yourself if possible.
Yeah. Hello, everybody. I'm fine.
Hello there. Assalamu alaikum. How are you, sir?
Walaikum assalam. Walaikum assalam.
Alhamdulillah. Alhamdulillah. I will just do a short introduction in Arabic if you may. السلام عليكم ورحمة الله وبركاته جميعا. حياكم الله جميعا في اليوم الأول من برمجون في نسختها الثانية. ولله الحمد نفتتح برمجون مع قائدنا جميعا والرجل الخفي تحت كل هذه الصعاب الأستاذ محمد عبد الباري. تعلمنا منه الكثير. الهدف من هذه الجلسات أن تكون الجميع المهتم في برمجة. هدف برمجون دائما وابدا أن نستسيغ عالم برمجي جديد يزيدنا إن شاء الله تفوق وعلم، وأيضا نعتلي جميعا في أن نجعل المبرمج السعودية يكونوا أكثر تفوق بمشيئة الله. ما أبغى أطيل عليكم الانترودكشن، بس حابين أقول لكم أنه اليوم في جلسة مع محمد عبد الباري. اليوم بكرة أيضا حيكون جلستنا الأخرى، ما أعلنا لسه، ولكن كونوا مشوقين في عبر حساباتنا التواصل الاجتماعي عشان تعرفون جلسة بكرة. جلسة بكرة لا تقل أهمية عن جلسة اليوم. دائما نسعد أن نتعاون جميعا في مجالات البرمجة. أي contribution أو تعليق أو أيضا استضافة أو إضافة دائما ما ارسلونا لنا يعني دائما نتقبل ملاحظاتكم. اليوم الثالث إن شاء الله حيكون مسابقة نهائية للمترشحين. دعواتنا جميعا لجميع candidates. Then, hello, Mr. Mohammed Bari. It's always a pleasure and honor to have you here with us. Our Twitter was so blooming yesterday when we posted your we revealed that you're coming. You're always a legend behind every CSIT student studying algorithms or anything else. It's always a pleasure having you here, sir, between us Saudi female and male students that are interested in tech. And Barmajon has always had the pleasure to have you within us. Thank you, sir, and the mic is all yours.
I'm glad to know that. Thank you. Alhamdulillah.
Okay, then you can share your screen, and I will leave.
I'll start sharing my screen.
Thank you, sir.
It's disabled, I think.
No, sir, not yet.
You have to. You have to give me access to the screen sharing.
Okay. Khalid, if possible. Sure, just a moment, please.
Okay. Yeah, I think I can do it now.
Okay, perfect.
Yeah, welcome everybody. Let us start with the session. The topic fundamentals of recursion, or I should call it as magic of recursion, or the importance of recursion. So in this entire 2 hours of session, I will show you what does it mean and what is its importance. All right. And this recursion we selected as a topic. We have had a discussion with your mentors, means your organizers. So I selected this topic because this is one of the topic where mostly students lag behind. They don't show much interest, or they get fear of this topic. So they are afraid of the topic. They think that is difficult, but actually the topic is very simple and very interesting. So I'll try to make the session so that you start loving recursion after the session. So let us go ahead. I'll be covering the topics like this. So this is the plan. So how it goes, it all depends on your feedback. Also, I want your I want to make the session a little bit interactive. If I ask any question, you should be able to answer it if it is possible. So if any one of you also answer it, that's enough. So I will be covering these topics like what is recursion, how recursion works, analysis of recursion versus loop, types of recursion, memoization, brute force, backtracking, dynamic programming. So let us go ahead now. So that is just the list. Now, let us start from here. What is recursion? See, first of all, recursion is a topic from mathematics. It's a mathematics topic. It's not a programming topic, very first thing. Now, how long you have been learning mathematics? You have been learning from your first standard onwards, like class first onwards, you have been learning mathematics. So you should love this topic. Instead of getting afraid of this one, you should love the topic because this is your primary topic. Programming you have started recently, but mathematics you have been learning from very long time, right? But mostly people ignore this one. They don't realize, they don't know that this belongs to mathematics. All right. So let us learn it as a mathematics topic. See, in mathematics, you have a topic called as functions, right? You have a topic called function. You write any function, for example, f of x is 2x squared plus 5x plus 4. This is a function. You put any value here in x. You put any value of x here, you get the result. So that's the result of a function. So similarly, in programming also, we write functions. So those functions are mostly related to mathematical functions only. The concept of functions in programming comes from the functions of mathematics. So let us define a recursion. What is a recursion? Recursion is a function which calls itself. A function calling itself. The function is defined such that it calls itself. So when it is calling itself means if you have called a function, for example, this is an example function. If you call it for value 5, then it enters inside, check the condition. If you see this function, it is printing the value, then it will call again itself with value 4. So again, the function is called. So again, it will be calling for 3, value 4, value 3, then value 2, then value 1, then value 0, then -1, and goes on. So it will be go on calling itself again and again. So when the function is calling itself again and again means it's like a loop. Yes, the function behaves, a recursive function behaves just like a loop only. It behaves just like a loop. So like in programming, you have something called as loop. You have a while loop and a for loop, right? But in mathematics, you don't have loops. So yes, recursion, we use it for performing looping operation, a repeating operation. All right, just let me finish this one. Then one more thing. As this loop, if you know from programming, a loop should terminate at one particular point. You should stop at one point. So same way, function should stop calling itself at some point. So for that, you require some base condition. Base condition is mandatory, right? Base condition. So this condition is called as base condition. So for any recursive function, there must be some base function, definitely. Otherwise, it never stops. It becomes an infinite recursive calls. So we don't write infinite recursive function. We make it finite. We must stop it at some point. So this is what recursion is. Recursion is a function which calls itself and it should have a base condition. And when it is calling itself, it should call itself with a changed value, different value. It should not call again itself with a 5 only. Like here it is becoming n-1. It should not be n once again. So if it is n once again, it never stops. Right? Now, if you have any question, somebody has raised a hand. If you have any question, you can ask me here. Al-Zahrani is raising hand. Do you have any question? Okay, I'll go ahead. Yeah, this was the introduction to recursion. What is recursion? Okay. Now, next is how recursion works. Okay. How it works. So how it works, to see its working, we have to trace this one. So one important thing is you should learn how to trace recursion. That is very important thing. And if you want to learn recursion, okay. Okay. So see, for understanding and learning recursion, to get the grip on it, you must spend some time by using pen and paper. So first of all, you should trace the recursion and understand it. So I will trace it and help you here to understand recursion. So let us see the working of this recursion. So first, let us see this function, what this function is. This function name is fun, and it is taking a parameter n, right? And this function is checking the condition first. If n is greater than 0, then it is printing the value of n. Then it is calling itself once again by reduced value of n, decreased value of n, right? If n is 5, it becomes 4. So there are two things that a function is performing. There are two steps inside this function. If this condition is true, okay, otherwise nothing is performed. If condition is false, then nothing is done inside the function. Now let us trace this function for some value. If suppose n value is 5, if we call this function by passing value 5, function of 5, if I call it by passing value 5, then what does it do? Function, I will not write complete word fun, I will write just f. Okay, so this will save my time and also it will be easy for reading the things. Now when I call this function by passing 5, it checks the condition is true. Because 5 is greater than 0, it will perform these two steps. So first step and second step. So for tracing a recursion, it will form a tree-like structure. 2 steps it's going to perform. The first step is what? Print n. So print the value of n. N is what? 5. And second step is, first step is over, completed, printed. On the screen it has printed. Second step is call it again by passing reduced value. So f of 4. So now for this function call, first step is over. Now second step, is it completed? No, it has to make a call. So again, it makes a call. So fun of 4 is greater than 0. Then inside these 2 steps are there. See, when we call fun of 5, it has not finished. First printing, second one, it should finish this step, then only this function ends. But this function is not yet finished. It has to perform 2 steps once again. So first step is what? Print 4. Okay, value of n is 4. Then call itself again for 3. Then third step, this step, again it is going to call itself, n is greater than 0. Yes, so again 2 steps. Print 3, call itself for 2. Then again 2 steps, print 2, call itself for 1. Again 2 steps, print 1 and call its step for 0. Now again 2 steps. No, not 2 steps. See now what value of n has become 0. Yes, 0 is not greater than 0. So it will not perform any steps. So this function ends. So which is the first function ending? This is the first function that is ending, right? So this function ends first. That's all. So what is printed on the screen? If I check so far, first 5 is printed. So output is what? First 5 is printed. Then 4 is printed. I am separating them by comma. All right. So you can read them. Though program is not printing comma, just I have separated them by comma. 5, 4, 3, 2, 1. So this is how it is printing. Now let me continue here. Function 0 has finished. Once it has finished, it will go back to the previous call. In the previous call, function of 1, value of 1 was n was 1. So it has finished printing 1 and also completed this function. So this function also terminates. Then it goes back to the previous call. And this 2 steps are completed now. So because this is terminated, right? So this function also terminates. It goes back to the previous call. Printing is done. F of 2 has finished. It goes back to the previous call. It goes back to the previous call. And from here, it stops. So the very one important thing is that if you see the recursion, working of the recursion, the 2 important things we observe here. One is the function is calling itself with 4. call itself with 3, call itself with 2, call itself with 1, call itself with 0. So it was calling every time. This was one phase of recursion. Then once it has finished fun of 0, it has terminated. So it went back to F1, terminated F1, went back to F2, terminated F2, terminated F3, terminated F4, terminated F5. So it was returning back to 1, returning back to 2, returning back to 3. So it was a returning phase. Returning phase. So recursion will have 2 phases. A recursive function will call itself, and then when it has reached the endpoint, because of the base condition, when it has reached the endpoint, it will go on returning now. It will go on returning now. So this is the very important behavior of recursion. So the powerful thing in recursion is its returning phase. Its returning phase. Now, how? I will show you. I'll take one more example. So I'll not go to next slide. I will take one fresh slide and I will cover this topic. Okay, I'll continue here. Now, suppose I'm writing one function, void fun, same function I'm writing, integer n. Okay, now here if I say if n is greater than 0, then now watch. Call function fun n minus 1, then print n. It's not printf. I'm not writing C syntax perfectly. I'm just writing pseudocode. Okay, print n. Now, what is the change from the previous function? I will just go back there and I'll show you. See here, the first step was to print the value of n, then call itself. So print 5, then call 4. But now I have made a change here. I have made a change here. Right? First step is what? First call itself with 4. If I'm passing 5 for the first time, call itself with 4. Then print the number 5. So how this works? Let us observe. If I call this function for the value 5, then f of 5. Let us see what happens. See, if the condition is true, it has to perform 2 steps. So it has to call itself first, then print 5. Now observe very carefully. See, the point is function is having 2 phases. So what are those phases? We have to observe clearly. If you understand this, then you have understood major part of the recursion. Okay, so observe this one. First step is calling itself with n minus 1, then printing. So first step, call. Second step, print. First step is call itself with f of 4. Printing? No. First finish this step, then do printing. Oh, so printing will not be done now. Yes, first finish this step. So in this fun of 4, check again. It call again. So n is greater than 0. Yes, again 2 steps. What are those? Call itself and print. So call itself for 3 and print. Printing? No. First finish this step. Okay, when to do printing? Afterwards. First finish this one. Okay. Fun of 3. 3 is greater than 0. So then fun of 2. Then print 3. No, not now. First finish this. Okay, we will continue. So call itself for 1 and then print. First call this one. Call itself for 0, then print. First finish this step. So fun of 0. When you call it for 0, 0 is not greater than 0. It doesn't do anything. And this stops here. So the function f of 0 terminates first. Then what happens? It goes back to the, just a minute. Let me change the color. Yeah, I got that. It goes back to the previous call. This has terminated. Yes. So one portion has finished. Yes. So for f of 1, first step is completed because the function has terminated. Now what is remaining? Print now. So now it will print this value of n. What is the value of n in this function? 1. So first output is what? It will print 1. Then this function terminates. It goes back to the previous call, returning. Then print 2. So 2 is printed. Then this function terminates, go back to the previous call. Now first step is over for f of 3. Second step, print now. So print. Then f of 3 finishes, terminates, it goes back to the previous call. Now f of 3 has terminated, so it has finished. First step is over. Now second step, print 4. So print 4. Now this 4, f of 4 has finished, go back to the previous call. right? So this step is over, now print 5. So this is how it works. Now you can see that this printing was done in which phase of recursion. If you observe this one, if you observe the first one, the printing was done in which phase of recursion? Sorry. Printing was done in which phase of recursion? Here, see, first it was printing, then call, print, then call, print, then call. So first it was printing, then calling. So we can say that printing was done at calling phase. But in this example, the new example, what I have given you now, I have just changed the order. Instead of first printing and calling, first I am calling, then printing. So what is happening when it is printing? Can you tell me in which phase it is printing? Can you give a chat message here? Yes, exactly. Al-Malki has given the answer. Yes, that perfect. It is printing in the returning phase. It is printing in the returning phase. Okay, got it. So that is important. So recursive function can perform something even at the calling time or even at the returning time also. So the most powerful thing in the recursion is it performs at the returning time. That is the powerful thing of recursion. All right. So in mathematics, problems are mostly solved using recursion only, not using loop. There are no loops in mathematics. All right. Now I'll write down one function, void fun, which is taking some parameter n, whatever it is. And if n is greater than 0, for example, so there is one line 1, okay, line 1. Then in line 2, it is calling itself fun of n minus 1, okay. Then in line 3, again, there is something. Can you tell me when this line 1 will execute and when this line 3 will execute? In which phases they execute? Can you answer it? Line 1 executes in which phase of recursion and line 3 executes in which phase of recursion? Very good. Line 1 in calling phase and line 3 in returning phase. Very good. Very good. Mashallah. Perfect. Line 3 in returning phase. That's it. All right. Now let us go back. Okay. Let us continue our topic. Analysis of recursion. Analysis means mostly we are interested in knowing the time taken by any program or function. So when we are writing a recursive function, we want to know how much time that recursive function is taking. We are interested in that. So how to measure the time taken by any recursive function? So I'll give you a quick idea on analysis, how to do the analysis of recursive function. So just now we have seen this function 5. When I say 5, then there was printing 5 and calling for 4, and then printing 4 and calling itself for 3, then printing 3 and calling itself for 2, then printing 2, then calling itself for 1, then printing 1 and then calling itself for 0. This is how we saw. Now, I'm interested in knowing the time taken by this recursive function. So how do you measure the time? Actually, the work done. So what is the major work done by this function? See, let us look into the steps detail. It is checking the condition. Okay, no problem. It is printing this one, then calling itself. So calling itself, but what is the work it is doing? Actual work it is doing? Printing this one. So major work is printing only. So printing just a value takes how much time? Printing a value takes constant time. Just one step. We go off one. Just one step for printing, right? Printing takes 1 unit of time. So this is taking 1 unit of time. One. Such how many such units of time it is taking? 1, 2, 3, 4, 5. So what is the value of parameter passed? 5. So it is taking how much time? 5 units of time for value 5. Then for value of n, how many steps, how much time it will be taking? N amount of time. So now listen. So what we do is, whatever the function may be doing, that is taking order of 1 time. Okay, so time is constant, not a problem. Then how much time, how many times that constant time is taken? So it depends on the recursive calls. how many calls it is making. So we basically count the number of calls mostly, right? So if you count the calls for 5, it is making total how many calls? 1, 2, 3, 4, 5, 6. Oh, why 6 calls? I'm passing 5. Yeah, for 0 also it is calling. No, so total 6 calls. So how many calls it is making? Calls it is making are n plus 1. It is making these many calls. So based on this, the time taken is what? Big O of n. So for analyzing recursive function, we trace it, and from the tracing tree, we call this as tracing tree. From the tree, we observe how many calls it is making, then we decide the time. Big O of n. Right? There is another way of doing this one also. I'll show you one more. There's another way of analyzing this algorithm. Let us see. Let us call the time taken by this recursive function as a t of n. Instead of f of n, we are saying t of n. So the time taken by this recursive function is f of t of n. Okay. Then how much time this is taking? 1 unit of time. I know that. Then how much time this may be taking? Guess. When you say this function is t of n, then what is this function is taking? This is taking t of n minus 1 time. Yes. So now, if you see what is the time taken by this function is the total time taken by all the statements. So what is the total time taken by all this statement? Tn minus 1 plus 1. I have added these two. So this is the total time taken by this function. And we are saying that the time taken by this function is Tn. So Tn is equals to Tn minus 1 plus 1. This is how we represent the time taken by any recursive function. And this is called as a recurrence relation. A recurrence relation. This is how we represent the time taken by any recursive function. So we define it right like this. Completely, I will write down now. Tn is equals to how much? Tn minus 1, sorry. Tn minus 1 plus 1 if n is greater than 0. But if n is equals to 0, it's not taking any amount of time. So you can say 0 also, or you can say 1 also. All right. So we usually write 1, we don't write zeros. Okay. So this is a recurrence relation. And if you solve this recurrence relation, you get the answer. And if you see the answer, obviously it will be n plus 1 only, and the time is order of n. So there are two ways of analyzing any algorithm. Listen very carefully. When you want to analyze the working time taken by any algorithm, one is through the tracing, you can observe and decide the time. Otherwise, from the code also, you can see the time taken by each statement, and you can sum up all of them and get the time taken by an algorithm. So if it is recursive algorithm, if it is a recursive function or recursive algorithm, then the time taken by it can be defined as in the form of recurrence relation. All right. And you have to solve this recurrence relation. How to solve, I guess you know this one. There are some YouTube lectures also. I have some lectures for solving this time, right? So I don't want to spend time on this solving, how to solve this one. Okay. Okay, let me quickly do this. Tn minus 1, right? Tn minus 1 plus 1. Then what is this Tn minus 1? Tn minus 1 is nothing but Tn minus 2 plus 1. And this one as it is, plus 1. Then what is Tn minus 2? Tn minus 2 is nothing but Tn minus 3 plus 1 plus these two, this 2 ones as it is, plus 1 plus 1. So if I actually add this, this is 3. So actually right now it is 3n minus 2, Tn minus 3 plus 3. So if I going on doing this, then at 0, T of 0, this will be n. How? When I say T of n minus n, this is plus n. And what is this T of 0? This is 0. T of 0, I said that we take it as 1. So what is the answer? 1 plus n. We got the same thing. By tracing the tree also, by observing the working of the algorithm also, we got the same answer, n plus 1. And from the recurrence relation also, we got the same answer, right? So there are two ways of analyzing algorithm based on its working. And I say that based on its working, if you are doing, that is perfect analysis, right? And the time taken is big O of n. So here also we got this n plus 1, and the time is big O of n. This is how we analyze the algorithm. Okay, I have some questions. Okay. Can you open the chat? Can you open the comment? Okay. And if n minus 1 was, no, this is a different thing. If you say if n minus 1 was n by 2, then again it will take 15-20 minutes for explaining that. Okay, I'll come to it if it is so. Okay. Acha, okay. Sorry. I have not read your complete question. Yeah. If n it was instead of n minus 1, if it was n by 2, it would be log n. Yes, perfect. You are right. Yes, perfect. You are right. Correct. I thought you are asking me to solve for n by 2, but no, you have given the answer. You're asking a question. Yes, it's perfect. Sure. Now, so the topic what I have covered is how recursion works. I have shown you there are two phases, that is calling phase and returning phase. And then I have shown you the analysis of recursion. All right. The next thing is recursion versus loop. Let us see what does it mean? What is the difference between recursion and loop, and which is better? Not better, we should say, we will compare that. Okay, we will compare that to get the idea. Let us see. See, recursive function is a function which is calling itself, so it will be keep on repeating the statement. So here is repetition, right? So here also repeating is there, repeating statements are there. Here also repeating statements are there. In both the places, repeating statements are there. So here also it will repeat. Call itself means it will repeat, go on repeating. So loop, if you read this is also repeating. Sorry, here, this is also repeating. Now you tell me, if I pass 5 here, okay, if I pass 5, so what is the time taken? Sorry, what is printed here? If I pass 5, so it will print 5, 4, 3, 2, 1. If I pass 5 here, so read this code and just tell me what it will print. So just read it. Okay, you don't have to answer and type the message. Just read it. There's a for loop, n I greater than 0, I minus print. So this will also print 5, 4, 3, 2, 1. Right? Okay. Yeah, same. Perfect. Now, observe. What I have done using recursion, can I do the same thing using loop also? Yes, I am able to do it using loop also. What I am doing using recursion, I am able to do it using loop also. So now listen one important thing. Whatever you can do using recursion, you can do it using loop. Whatever you can do it using loop, you can also do it using recursion. Right? Keep this thing in mind. All right. Almost every recursion you can convert into loop. Every loop you can convert into recursion. This is the first point. So you can see one of the example I have shown you. Okay. Now, how to convert? It needs a practice. Okay. There is no formula. Got it? So there is a practice. Means if you go on doing it, then you get the idea how to convert every recursion into loop. Now, next thing. When we have loop, why do we need recursion? Or when we have recursion, why do you need loop? So listen. Recursion are available in mathematics and loops are available in programming. They are available in programming. Okay. For mathematics, recursion is available in mathematics, loops are available in programming. Now I have one simple question here. If any problem is there, who solves the problem? Or how do you solve the problem? Using mathematics, you solve the problem, or using programming, you solve the problem. As an engineer, if you are an engineer, how do you solve a problem? By applying mathematical skills or programming skills? Don't say programming skills. Don't say programming skills. It's mathematical skills. A problem can be solved by applying mathematical skills, not programming skills. All right. Now, if you are a software engineer, you apply programming. If you're a civil engineer, then what do you apply? So always the problems are solved by applying sciences, maybe mathematics, maybe physics or chemistry or any other thing. You apply sciences for solving the problem. And engineering is doing some project or doing some work by applying sciences. So for solving a problem, we use mathematics, right? So it means the solutions that you get, if there is any repeating solution, then definitely it will be in the form of recursion only, not in the form of loop. All right. So mathematics is there from centuries long, right? People have been practicing mathematics from long time. Programming came recently, right? Not even 1 century old. So this is a very old thing. So people have written a lot of recursive functions are there in various areas of mathematics. Now, when programming came, there's a lot of work to do, right? Programmers have converted these recursion into loops. They have converted the recursions into loop. Now, why converted into loop? Doesn't the programming language supports recursion? Yes, programming language supports recursion, but recursion takes more time compared to loop. Why recursion takes more time compared to loop? Because recursion, it involves or take more times because it has to make a call, make a call, make a call. So calling a function takes little bit extra time. There are more issues, just I don't want to go in detail. Just I'm telling you one important point, that as a recursive function, it has to make a call once again and again. So calling a function takes extra time. All right, got it. And there is a famous thing, like recursion uses a stack, because for every function call, it has to make a stack entry. So for every function call, stack entry is required. All right, if n is there and the function is calling, if I pass 10, then 10 to 11 stack entries will be created. So the value of n will be stored for 11 times, for 10 and 9, and for every function call, a new stack entry is maintained. So this consumes a lot of memory as well as time. Right? Now, if it can be converted into loops, then our machine can execute faster. That's how recursions need to be converted into loops. That is the requirement. Understood this one? So once again, I repeat the point. See, when you give a solution, you must give a solution in the form of recursion. Then solving a recursion is time consuming. But in programming, we have loops. So we try to convert a recursion into loop. Then we write the programs in the form of loops. All right. Maybe you have heard of dynamic programming, DP. There's a famous topic, right? Every software engineer talks about DP. What does dynamic programming do? In dynamic programming, one of the aspects, there are a lot of aspects, or there are a lot of points about dynamic programming. One of the point in dynamic programming that we solve recursion using loops actually. Okay. Dynamic program can be defined in various ways. There are various things. Okay. So if time permits, I will cover that. So one of the important thing is that dynamic programming solves a recursive problem or recursive functions using loop. All right. So this is the difference between, okay. Yeah, uses more space. Mo had said that in DP, we use both. In DP, actually, we write recursive function, but we don't solve it in the form of a tree. We don't solve it in the form of a tree. We make a table and solve it. That is nothing but we are using loop. Okay. So recursion is solved just like a loop. I'll explain you about that one. Okay. Now, is it okay till here? Is it okay till here? Everybody is following? Yes. Okay. Clear. Yes. Is it useful? One more point. I am more interested in knowing this one. Is it useful? Or is it just the basic which you already know? Okay. That's great. Now, there are different types of recursion. So quickly I will cover this. See, suppose you have a recursive function. I will write on the function name as fun only. Okay. For explaining this one. Then inside this, the condition is if n is greater than 0. Function can be anything, condition can be anything. Okay. But I am consistently taking similar example to help you with understand this one. Now, there are some statements here, maybe printing or doing some calculations, whatever it is doing. Then the function is calling itself with a reduced value. So it may be n by 2 also, or n minus 1 also, or n by 4 also, n minus 2 also, right? So it can be anything. So I'm taking n minus 1. Now these statements are there. First, they are executed. The function at the last statement in the function is, it is calling itself. Last statement in the function is, it is calling itself. First, it is performing all these steps, first step, second step, third step. Then after that, it is calling itself. So the function is calling itself, and that recursive call is the last statement in the recursive function. So we call this type of function as a tail recursion. Tail recursion. All right, tail recursion. Now, hope you understand what is the importance of this one, why we are talking about this type of recursion. When the last statement is the function call, then all the work done by this function is done in which phase? The work done by this function is done in which phase? Yes, you are right. It is done in calling phase. Yes, it is done in calling phase, right? I know what the answer you have given. Oh, sorry. Calling phase. Yes, you are right. Okay. So I just gave you time to answer that one. So it is doing everything in calling phase. So when it is doing everything in calling phase, let me go back. One more point. I missed that actually. Sorry for missing that. Let me come back. Now, if you see recursion, recursion is having two phases, right? We know that this is having calling phase and returning phase, right? It is having calling phase and returning phase. But what about loop? Loop. Repeat, 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 stop. That's all. There is no go back, go back, go back. There is no returning phase. So loops have only, I should call it as calling phase. So instead of calling, we change the statement. Now we change the word. This is ascending phase. Okay. And this is descending phase. So recursion is having two phases. Call, call, call means it is like ascending. Okay. Then return, return, it is descending. So, but loops have only which phase? Ascending phase. Loops have only ascending phase. All right. So now if you observe, compare recursion versus loop, who is more stronger? Recursion is more stronger, right? If you say, because you can do a lot of things in descending phase, but loops have only ascending phase. Now come back. Now, what do you call to this calling phase? Just now we said that this is ascending phase. So ascending phase is there in the loop also. Yes. Now listen, the important point. If you are writing a tail recursion, then it can be easily converted into loop. Easily converted into loop without any efforts. Easily converted into loop. Yes. All right. So if there is any tail recursion, it can be easily converted into loop. Now, let us go back to the next type of recursion. Next type of recursion. This is void function fun. It is taking n. Now, if n is greater than 0, right? Now, first the function is calling itself. The very first statement is the function call, recursive function call. Then it is performing all the statement. So all the work is done by after the function call. So everything is happening at which phase? Everything is happening at returning phase. Returning phase. All right. So because the very first statement is the recursive call. So that's why we call it as head recursion. If it is anywhere in between, then it's just a recursion. Okay, there is no speciality of that one. But this one is a tail recursion because the last statement is recursive call. This is a head recursion because the very first statement is a recursive call. Now, when you want to convert this this head recursion into loop, when you are going to convert it, then mostly we have to use a stack. We should maintain a stack. All right. Now, let me show you why we need to maintain a stack. See, here, if you see this recursion, can you tell me which recursion is this one? Head or tail recursion? I'm waiting for your answer. Head or tail recursion? Head. Very good. Very good. Yes. 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 Thank you for answering. Yes, this is head recursion, right? Now in head recursion, you observe that when the function terminated, it went back and required the value 1, then 2, then 3, then 4, then 5. So it needs these values. It needs these values. When returning, it needs the value. So what we have to do is, if you're using a loop, then what you should do? 5, push it into the stack, then make 4, then push 4 into the stack, then make 3, then push 3 into the stack, then make 2, then push 2 into the stack, then make 1, push 1 into the stack, then make 0. Now return back. Returning part, how you can do? Take out 1, so print 1, take out 2, then print 2, take out 3, then print 3, 4, then 5. If you're converting this into a loop, then you may require, not always, not necessary, maybe it is have possible without stack also, but most of the time it requires stack. So if it is a head recursion, then you need a stack. Okay, so when you want to convert a recursion into a loop, then it depends on the type of recursion. If it's a tail recursion, it can be easily converted into loop without any stack. If it is head recursion, then you may require a stack. Then lastly, tree recursion. If you have a recursive function, void func int n, then if n is greater than 0, then function call. Okay, I'll do one thing. I'll just print the value n. Okay, print the value of n. Then I will make a function call but n minus 1. Then again a function call with n minus 1. So function is calling itself, right? But if you observe, the function is calling itself how many times? 1 time, 2 times. So if you see all the statements, first one is print, second one is call itself, call itself. So it is calling itself 2 times. So if a recursive function is calling itself multiple times, more than 1 time, then it is called as tree recursion. Tree recursion. Right? These are little complex recursion. So when you want to convert them into loop, then little complexity is involved. And there is no formula how to convert a recursion into a loop. Every recursion you should observe and apply your own analysis, observation, and your own intelligence and knowledge. You have to convert it. Okay, so that comes with experience. If you go on converting them, you get experienced, and then you can easily convert them. All right. So if it's a tree recursion, then it becomes a complex thing. So again, if you talk about DP, mostly in dynamic programming, we use tree recursions only. A function, recursive function, will call 2 times, 3 times, or 10 times, or multiple times it calls itself. Recursive functions, they call themselves multiple times. Right? So that's it. This was about the types of recursion. Any questions still here? Yes. Okay. How can you analyze the time complexity of recursive recursion? Tree recursion. For analyzing the time taken by this tree recursion, if I say the time taken by this function, actual function is Tn, then I should find out the time taken by all the steps inside. So this step takes 1 unit of time. This step takes n minus 1. If it is minus 1, it is n minus 1. If it's n by 2, this is n by 2. Okay. Then this is also n minus 1. So if you sum up all these, you get the time taken by this total function. So this is, see, this is function fun, right? So you are saying Tn. So function fun of n minus 1 is n t of n minus 1 only, right? So the time taken by this function is Tn is equals to, Tn, sorry. Tn minus 1 by 2, Tn minus 1 by 2. So this is 2 times T of n minus 1 by 1 plus Tn minus 1, Tn minus 2 times. So then also 1, okay, if n is greater than 0. Otherwise, if n is equal to 0, then nothing, so say constant. So this is the time taken by this recursive. This is the, okay, this is the recurrence relation of this recursive function. All right. Now, other ways, you can draw a tree and you can count how many calls it is making. Then you can get the time taken by this function also. Okay. And if you solve this particular one, the one which I have shown you, if you solve this take 2 power n. This takes 2 power n time. All right. Let me do one thing. This may help you. I'll remove this. I need a space here. Okay. I need a space. So you have already seen this one. I'll remove this. Now, somebody have asked the question that how to analyze this one. So a good question. I'll do it quickly. So you get the idea. Okay. Now, let us call this function. Okay. For value 4. Function for value 4. What are the steps? 3 steps. First step is printing. Second, call itself. Third, also call itself with value. Reduced value. So first it will print 4, then it will call for 3, then again it will call for 3. Then first call, we have to finish this first call. Print 3, then call for 2, then again call for 2. Now I cannot write brackets because it will look congested. Okay. Then first finish this one. But we know that first it has to finish this one. But for this also I will draw it. Okay. But because we are analyzing, we are not interested in what is the result. Okay. So this also will print 3, then call itself for 2 and call itself for 2. Okay, first this call executes. Print 2, call itself for 1 and call itself for 1. Okay, and here also print 2, call itself for 1, call itself for 1. For here also print 2 and call itself for 1 and call itself for 1. Here also print 2 and call itself for 1 and call itself for 1. But all these happens afterwards. First of all, this is done. So call itself for 1, print 1 and call itself for 0, call itself for 0, print 1, call itself for 0, call itself for 0. This is 1, print 1, 0, 0, 1, 0, 0. I'm not writing F also now because I don't have space here. So this is calling itself for f of 1. Okay. Print, print 1 and call itself for 0, call itself for 0. Print 1, call itself for 0, call itself for 0. Print 1, 0, 0, print 1, 0, 0. If you count the calls, this is 1 call. If you count these calls, 2 calls. If you count in this level, how many calls it is making? 4 calls. If you count in this level, how many calls it is making? 8 calls. In this level, how many? 16 calls it is making. If you add all these, this is nothing but 1 plus 2 square plus 2 cube plus 2 power 4. So if you add 1 plus 2 square plus 2 power 3 plus 2 power 4, then the answer is 2 power 5 plus 1. Means 2 power 4 plus 1 plus, 4 plus 1 minus 1. Okay. 2 power 4 plus 1 minus 1. That is the answer. So up to 4, it is 2 power 4 plus 1 because I have passed 4. So up to n, what will be the answer? 2 power n plus 1 minus 1. So I have counted the calls. So the total calls are 2 power n plus 1 minus 1. So this is what? Plus 1 you can ignore. You can say bgo of 2 power n. That's what I said. The time taken when you solve this one, you will get the answer as 2 power n. This is how we solve it. If you add them, you can see that this is 16 plus 8 is 24. 24 plus 4 is 28. 29, 30, 31. So 31, what is 31? 31 is nothing but 32 minus 1. Okay. What is 32 minus 1? 2 power 5 minus 1. Yeah, that's what 2 power 5 minus 1. So when you add the series of powers of 2, you get 2 power n plus 1 minus 1. This is the formula, right? This is the formula. So that's how I have done the analysis. For 4, I have done it and I have given a generalized answer. Okay. If you're not sure, no, this may be wrong. So do it for 5 also and check it. Okay. But when you are writing a formula recurrence relation, then you can easily solve this one. Is it okay till here? I think, yeah. Okay. Yeah. Now let us move ahead. Now I will cover one important topic in the recursion. Okay. That is memoization. Memoization is one of the important topics. okay, in recursion. See, this is a Fibonacci series. Fibonacci series or Fibonacci series. Okay, so this is a Fibonacci series. And Fibonacci series starts from 0. Is it 0 or from 1? Okay, 0th term is 0. First term is 1. If you start writing from first term, it is 1 onwards. If you start writing from 0 term, it is from 0 onwards. Okay, basically you should start from 0. So first two terms are 0 or 1. Next term is by adding, next term is adding. You know this one, I don't have to explain, I guess, right? So every term is obtained by adding previous two terms. How you can define this in mathematics? Fibonacci of n is what? Fibonacci of n minus 1 and n minus 2. These are nothing but previous two terms. If n is greater than 1. If n is equals to 0, the term is 0. If n is equals to 1, then the term is 1. Otherwise, we add two terms. So very first two terms are what? 0 and 1. The other terms are addition of previous two terms. So the same thing is defined mathematically in the form of a function like this, right? And I have written a C program or a pseudocode also, right? For the same thing. If n is less than or equal to 1, return 1 n itself. Means if it is 0, return 0. If it is 1, return 1. Otherwise, call this function 2 times. All right. Now, can you tell me which recursion is this? Which recursion is this? We have seen 3 recursions, right? Types of recursion. Which type of recursion is this? I need 2 answers. Okay. First, listen. Which type of recursion is this Fibonacci? Fibonacci, which type of recursion? First question. Second question, if I pass n, what is the maximum time taken by this one? Can you answer these two? Sorry. Exactly. Exactly. It's a tree recursion. Very good. It's a tree recursion. Abdullah has given the answer. Yeah, tree recursion 2 power n. Very good. Very good. Thank you for answering. So, yes, it's a tree recursion. Function is calling itself 2 times. So it's a tree recursion, right? Then the second thing is, just now I have shown you that this was calling itself 2 times n minus 1. So we got 2 power n. But this is not calling itself by n minus 1 both the times. It is calling itself one time by n minus 2. So for n minus 2, what is the time you get? If you try to analyze this, this becomes very difficult and tough for getting the exact answer. What we say that, oh, this is too much. Let us call it as n minus 1 only. So don't say n minus 2. Let us think that it is n minus 1 only for analysis purpose. For analysis purpose. If you do that, then it's a direct answer, 2 power n. But is it the exact analysis of Fibonacci function? No. That's why we say big O of 2 power n. What does it mean by big O? Upper bound. Upper bound. So we have not done the exact analysis of this one. Just we saw the function and you said that 2 power n. And yes, that's the answer, correct answer only. But it is not the exact answer, right? If it is n minus 1, that is an exact answer. So it is less than 2 power n. How much less? Oh, that doesn't make any difference for us. It's almost 2 power n only. Yes. So we are happy with the answer 2 power n. So when we do analysis, we don't want exact figures, exact results, right? We want approximate results. We want approximate result. Okay. When it was given, okay, 1 hour. Okay. All right. That's why the term big O comes. I have given you one more reason here. One more point I'm telling you that big O means the upper bound. Suppose you have an algorithm and say that the algorithm is taking big O of 2 power n, means at most it is taking 2 power n. It may be taking less than that also. it may be taking less than or equal to that also, but not more than 2 power n. That is the meaning of big O. If you say omega of something, let us say n, means minimum it is taking n time, not less than this. If you say theta of something, or say, let us, if you say theta of 2 power n, when you say theta, it means exactly 2 power n, right? Not more than, not less than. So when you use theta, when you know the exact answer, there is no difference at all, then you use theta. So mostly in the industry and in education also, we commonly say, in academics also, we commonly say big O. Big O means we don't want to take a chance. Nobody should catch your shoulder and collar and ask you how it is theta. So to feel safe from that, we say big O of 2 power n. Right? Big O means upper bound, you are saying. That's the trend. All right. So these are the things. What? Let me remove this from. Okay, let us go back. Now, I have this function. I have this function. I will trace this function because I have to explain memoization. Actually, from the memoization, you get the idea of dynamic programming also. So from memoization, you can understand that you can understand the one of the important trick in dynamic programming also. Okay, and dynamic programming, there are a lot of things in dynamic programming, but at least you'll feel comfortable with one of the important aspect of dynamic programming. You feel comfortable with that one. Okay, now listen. This is a Fibonacci function. Okay, I want to find out fib of 5. So I'll just write f instead of writing fib. Fib of 5. Okay, got it. Now I will trace this one. I will trace this one. Let us see this one. This is 5. Okay, 5. 5 is not less than 1. So it will enter into else part. So for all the values less than or greater than 1, it will enter into else part and it will make 2 calls. Okay, so first call and second call. Got it? First call, it's what? Fib of 5 minus 2 and 5 minus 1. So whatever the value is, minus 2 and minus 1. So this is 3. Sorry. Yeah, 3. And this is fib of 4. 2 calls it is making. I'm going to trace this one. So it's a tree recursion. So let us do it. Got it? Then later on, it is going to add. Addition will be done when? First call this one, return back and call this one, then return from this one also, then add. So at last we'll be adding, not now. Now, first we will make this call. What is this? Fib of 3, it's greater than 1. So make 2 calls. Fib of 3 minus 2 is 1. Then 3 minus 1 is what? 2. Later addition will be done. Later we will do. First make this call. Fib of 1. Fib of 1, it is equal to 1. Return 1. So the result of this function is 1. So I'm writing the result directly here. So this is equal to 1 actually. This function became equal to 1. All right. Now this function has terminated because it has entered into if part and return 1. That's all. Then make a call on this one. This one. It's greater than 1. Okay. So again, it has to make 2 calls. Fib of 2 minus 2, 0. Fib of 1. Now I'll do quickly. Okay. I'll do quickly. Fib of 0 is 0. 0 is less than 1. Yes. So 0 is less than or equal to 1. Yes. So it returns 0. So the value of this function is 0. Then it makes this call. This call again, fib of 1 is what? 1 only. 1. Now this call is also over. So it has first made this call and this became 0 and went back and called this one and this also became 1 and it will return back. Now it has to add these 2. So 0 plus 1, the answer of this function is how much? 0 plus 1 is 1. Now for this function, if you see, this is also over, this is also over. So it will add these 2 and the result of fib of 3 is how much? 2. Then it will come on the right hand side. If you see the order of the function call, this was the first call, this was the second call, this was the third call. Go back, this is the 4th call, this is the 5th call. Then go back, this is the 6th call. Then go back and this is the 7th call. This is how the calls are being made. Okay. Now for 4, it will call itself for 2 and it will call itself for 3. Yeah. Is it? Yeah, perfect. For 2, again, it will make a call for 0. Again, it will make a call for 1 also. For 0, it is 0. For 1, it is 1. Then the answer is added here. So this is again 1. 0 plus 1, they are added. So this is actually 0 and this is actually 1. So 0 plus 1, they are added and the result of this function is 1. Okay. Then it comes on this side. This is f of 1. Yeah. This is f of 2. F of 1 is 1 again, f of 2 again, it is making a call, f of 0, then f of 1, then again this is 0, this is 0, and this is 1, and this becomes 1, and this is 1 plus 1, this becomes 2, and this is 1 plus 2, this becomes 3, and this 2 plus 3 becomes 5. So the result of this function is 5. So if you continue with the calls, this was 7th call, this was 8th call, 9th call, 10th call, 11th call, 12th call, 13th call, 14th call, and this is the 15th call. So total, it is making 15 calls for solving this problem. It is making total 15 calls. All right. Got it. So the entire tree is here. You can see how it is working. You can see the calls and you can check how it is working. Yeah. So these many calls it is making. Now, if you observe in this one, observe this one. See, this is fib of 3, right? Entire tree. This is fib of 3. Now, first time when it has already known fib of 3, then why it is calculating fib of 3 once again here? In this side also, it is getting fib of 3. Why it is wasting time? Oh, so it means if there is any possibility of saving time, yes, you can save the time by to make the calls once again. Now, if you observe more deeper, fib of 2 is called here also here. Oh, fib of 2 is called 3 times. It's calling 3 times. So why it is calling so many times? So instead of that, can we do something to save the number of calls? Total 15 calls were made. Can we save the calls? All right, this is the idea. So yes, what we do is we will keep an array. Okay, we will take one array. We are going to find out fib of total 5 values. So this requires 0, 1, 2, 3, 4, 5. So this 0, 1, 2, 3, 4, 5. Okay, I got 6, leave it. So just leave it. This is not no use. So 0 to 5. Okay, I am taking one global array. Initially, I'll fill these values with -1. Okay, -1. So these are all -1, -1. Now, any question? Okay. Now, let me finish this. Now, I am taking you towards memoization. So what was the point? I said that it is making so many calls. So and some calls are repeating. We want to avoid that repeating calls. So what we can do? Let us see here. Now, let me call this entire tree tracing. I will do it once again. I have a global array called F, and that is having indices from 0 to 5, and all are initialized with -1. Let us start. Fib of 5. Shall I call this function? Yes. Fib of 5 is having -1 because I don't know the value of 5. I will call the function. So first call, this is done. Then it will go to this call, right? Fib of 3. 3 is -1. I don't know the value, so I should call this one. This function is called. So inside this, again, this is the next call. Fib of 1. I don't know the value of 1 because it's -1. I should call this function. So now I call the function. The result of this function is 1. So I will modify this function, modify this value and make it as 1. Now I know the value of fib of 1. Now this is over. Go back. So total how many calls I made? First call, second call, third call, 3 calls I made. I go back, right? Then I should make this call, fib of 2. Do I know fib of 2? No, I don't know. I should make the call. So I make the call. Inside this, there are 2 calls. So first call, fib of 0. I don't know. I will make the call. So I will make this call and this becomes 0. Result. So whenever I'm getting the result of a function, I'm saving it in an array. I'm saving it in an array. Okay. So this is now 0. Now come back. Fib of 1. Should I make this call? Check fib of 1. I already know the answer. No need of making this call. Oh, time is saved. This already I know the answer. So how I can get the answer 1 from where I can get? I get it from array. So 0 and 1 I will add. And now f of 2 also I know the answer. So I will write down 1 here in f of 2. I got this answer also now. Okay. Then go back. Now I can know the answer of fib of 3 also. From the array I will take. This is 1 and this is 1. This is 1 and this is 1. And the answer is 2. Fib of 3 is a 2. I have filled the result in the array. All right. Now go back. Fib of 5. I cannot add these two results. I don't know a fib of 4. So let us go to fib of 4. Shall I make a call? Yes, I don't know fib of 4 because it's -1. Make a call. So once I call this one, again, it has to decide two calls. Fib of 2. Should I make this call? No, because already I know the answer. When I am not making this call means these are all also discarded. They are not done. Then I will go on the right-hand side. Shall I call fib of 3? No, already I know the answer. No need of making all these calls. These are all cancelled. When I don't call fib of 3, further calls will also be not called, not done. Then how I can know the value of fib of 4? Fib of 3 is 2, fib of 2 is 1. Add them, result is 3. So in this add, store result 3 now. Now I know fib of 3 also, 4 also, update this table and make the result as 5. Now you count how many calls I made, total how many calls I made, right? I just made one call, this one, 1, 2, 3, 4, 5, 6. Only 6 calls I made. For which value of n? 5. So for n, I made how many calls? For 5, I made 5 plus 1 calls. For n, I will be making n plus 1 call. Why 1 extra? For 0 also there is a call. No? For 5, 4, 3, 2, 1, as well as 0 also. So n plus 1 calls it is making. Now you can see that I have suppressed the recursive call, discarded the recursive call, avoided the recursive call because I am maintaining the value in the table. I'm maintaining the values in the table. So in this way, you can avoid the repeating calls. So if you find any repeating calls in the recursive function, then you can avoid them by storing the results in a sum array, global array, keeping the storing the values of that recursive calls and reuse them again in further. Whenever you have to make a call, avoid the call and directly use the value. So making this table is called as memoization. Memoization means identifying or marking. Okay. You can also say memorization, but it's not memorization, it's memoization. Memoization is also recognizing or storing or marking like thing. So we are marking the values. Okay, that's how it is called as, famously known as memoization. So you can see that this recursive function, which was taking 2 power n, we go of 2 power n. Now I have used memoization. I have to rewrite the recursive function. I have to change the recursive function here. Okay, it will not be like this. So when I change the function, the time taken by this function will be n plus 1. So this will be big O of n. From exponential time to polynomial time. So there is a good reduction in the time taken by this function for solving the problem. Fibonacci problem can be solved in n time now instead of taking 2 power n time. All right. So that's how memoization gives the idea that if in a recursive function, if there are some repeating calls, you can save the time, avoid those repeating calls, and store the result in the table. All right, store the result in the table. Now, one more thing. And this, understood this one? Now, by using the table, you can reduce the recursive call. Now, observe one more thing. Listen carefully. This is recursion. Okay. If I trace this, I get a tree like this. But I have used memoization, so I should change the function. This will not be the same function. This is a change one. Okay, I have not written it. So which will reduce the call. So it's order of n. Now, if you observe, to get the value of f of 5, to get the value of f of 5, right? I should know f of 3 and f of 4. For 3, I should know 1 and 2. For 2, I should know 0 and 1. So it means first I should solve which one? First of all, directly start from first solve 0, first solve 1, then solve 2, then solve 3, then 4, then 5. Oh, it's easy. I know that in the recursion, I can know the result of f of 5 only if I know 3 and 4. So for solving, you don't even follow the tree. You just make a table, box-like thing, table-like thing, and start filling the value. For f of 0, put value 0. F of 1, put the value of 1. Then for 2, you can add previous to value and store it previous to value. Like the way how we have filled the values here, fill the values here. So this filling, you tell me, this filling directly, 0, 1, add previous to values as previous to values. This filling, is it done using loop or recursion? Can it be done using loop? Simply just previous to values and store it. This filling of values in the table is done using loop or recursion. Do you really need recursion? Just I need the answer here. Just filling the table. Okay. Exactly. There is no need of any recursion. Just this can be done using loop. Yes, exactly. It can be done using loop only. All right. So that's how dynamic programming works in the same way. The formula is a recursive formula in dynamic programming always. The formulas are always recursive because the solution is given in mathematics. So the formula will be recursive. But we don't draw this recursive tree completely. We see that we start solving the problem from smaller problems. Then we get the solution from large problem automatically, right? So that's what we do in dynamic programming. We fill the table directly. If you see DP problems, all of them, we fill the table. And sometimes you don't understand how that table is filled. Just blindly follow the method, do it. But actually, if you observe, you are doing recursion only. That is the reason filling the table, why I should fill it like this. You get confused there. The confusion in the dynamic programming topic is that one only. If you're learning the known problem, then actually you're following recursion, but you're not tracing it in the form of a tree like this, but you are filling the table, right? You start filling from smaller values when you need the larger value. Okay. Is it okay till here? Have you understood everything till here? We move ahead. Abdullah is asking some question. Let me read out. Yes, but when I should use when I should use recursion instead of loops, if you can always convert it into loop, a loop is that's what I have answered your question only. If you have understood, just reply me. I said that problems are solved or the solution of a problem is given by writing mathematical function, and the function may be recursive function also. If it is a recursive function, then for getting the answer, we don't do tracing sometime. If there is a repeating problem, we don't do tracing. We try to find the smaller values and fill the table to get the actual answer. We use loops. First, loop doesn't come first. Loop doesn't come first. First, recursion comes. Then how to solve that recursion? We follow a faster and easy trick, that is using loop. Abdullah is asking that when I should use recursion instead of loop, if you can always convert into loop. Every recursion you convert into loop and use loop only. That's what I am saying. All right. Have you understood the question? Okay. You got my answer? Have you understood my? Is it always big O of n when using? No. It's not big O of n for always big O of n for memoization. It is big O of n for Fibonacci function when using memoization. So it's only for Fibonacci. In some other cases, it may be n square also. It may be n square also. It may be n cube also. It depends on the problem. Okay. See, mathematical work is done from very long time. A lot of people many people, mathematicians have written functions, recursive functions. So programmers are converting them. Still a lot of research is going on. We try to convert recursion into loops. So DP is one area where you solve the recursive function only, but by filling the table, by using a loop, okay, in the form of a loop. So it's an easy way of solving a recursive function. Instead of drawing so much big tree and solving it, we do it using table. Okay, so actually we are solving recursion only, but using loop. Hope you got this one. Now, do you have any questions? I will proceed further. Okay. Now let me discuss something powerful in recursion. That is the one of the powerful thing in recursion. Okay, after this, yeah, I have backtracking also. I'll explain. Then also, what is actually dynamic programming? I'll explain you. Okay, finally. So these are the three things remaining. So now, brute force. Yeah, everybody following? Do you have any questions? Okay. Yeah, let me explain. See, what does it mean by brute force? Brute force means exploring all possibilities. Exploring all possibilities is nothing but brute force. Okay. Like mostly you might have heard that hackers will hack and guess a password by using brute force. Right? Have you heard this one? Brute force means finding out all possibilities. Finding all possibilities, nothing but permutations. Permutations. So brute force is just like permutation only, finding all possibilities. Permutation means if you have some set of items, you can find various arrangements of items. It's nothing but permutation. But it may not be permutation always. I'm saying possibilities. Trying out all possibilities is nothing but brute force. All right. Now, so permutation also comes under brute force. Now, suppose, let us understand how this brute force works. If I have alphabets A, B, C, right? Now, what are the permutations? A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. These are the permutation. How you can obtain all these permutation? So let me draw them in the form of a tree and show you. Okay. So I'll draw a tree. Start from here. First, there is nothing. Okay. There's nothing. First one. I have selected A. Then I am labeling edges to show the selection of alphabets, not vertices. I'm not putting them in nodes. Okay, I am labeling the edges. So selection is shown in the form of edges. I am selecting A. Then I selected B. Then I select C. So I got what? A, B, C. Go back. Go back. If I go back here, already A, B is selected. Is there any alphabet remaining? No, nothing is remaining. Only C was there that I selected. Okay, so go back once again. Now, if I go back, A is selected. Till here, A is selected. Then I selected B. So instead of B, can you select C? Yes, you can select C also. Once I select C, what is remaining? I can select B. Sorry, I can select B. So what it becomes? A, C, B. All right, I'll redraw this one. So this means this was C. Okay, C. So this was A, B, C. C, when I have selected A, B, and C, I got the permutation A, B, C. I went back and changed B to C. Then I got a new letter B. So this is A, C, D. Then go back from B. There is no letter. Go back at this point. Now B and C both I have tried. Go back to this place. Now I have already selected A. Now I can select B. When I select B, next I can select A. Next I can select C. So this is B, A, C. Go back. And at this place I can select C. Then I can select A. So is it not recursion? Don't you see it as a recursion? Yes, this is a recursion only. This is B, C, A. Then go back, right? Only A was there. Go back. A, C, I both have tried. Go back. Here, A, B, I have tried. C is remaining. See, Once I select C, next is A, and next is B is remaining. I'll take this one. So C, A, B, C, A, B, then go back, then here, instead of A, I can select B. Then when I selected B, the remaining letter is A, I will select that. So C, B, A, C, B, A. 1, 2, 3, 4, 5, 6. I got 6 permutations. I am showing these permutations in the form of a tree, right? So I said that select A, select B, select C, go back, select C, going back. So it is just like calling and returning. So this can be solved using recursion, right? So for finding permutation, we can refine a function which will be a recursive function, right? So finding all possibilities, right? I have found all permutation is nothing but brute force. So this is nothing but brute force only, right? Generating all possibilities is brute force, and brute forcing is done using recursion. Brute force is actually means what? Brute force, if you see the meaning, brutally applying force means you are penetrating deep into. That's the meaning. You are penetrating deep into, means exploring all possibility. That's how the meaning is, right? The term is little barbaric, sounds like, yeah, but it's brute force means penetrating deep into. So we have found out all permutations by using recursion. So brute force always use recursion. Brute force have different meaning. Recursion is different. Recursion is just a recursive function. Brute force means using recursion. Brute force means finding all possibilities. Can you do it using loop? Maybe you can do it using loop also. But mostly brute force means we use recursion. This one point. So I have one example. A function is there. Okay, this is a function. Now this is ABC. Now, how to find this permutation of this one? I have written the code here also. If you want, you can take the screenshot and you can try this tracing of this function. You can see that it will find the result in this res array, res array. And it will print the result. Whenever it is getting the result, it will print the result. So you can see this, I have written this brute force function for performing brute force, a permutation function, and you can see that it is calling itself, right? It is calling itself again. So this is a recursive call. This is a recursive call. From here, it is calling itself, okay? And this recursive call is inside loop. So how many times the recursive function is calling itself? Is it one time? No. 2 times. If it is 2 power 2 times, then it is 2 power n. You remember, one time I have shown you. So if the recursive function is calling itself 3 times, then it will be 3 power n. But it is not calling 3 times also. It is inside for loop. Can you guess what is the time taken by this permutation? Guess. Let me see how many can answer it. If a recursive function is calling itself 2 times, it's 2 power n time. It will take 2 power n, big O of 2 power n. 3 times means big O of 3 power n. But it is inside for loop. So guess how many times it is calling and tell me what is the time taken for such a function. Here it is 3 alphabets. So for this example, it is 3 power n. For any string, what will be the time? Nobody have answered. Okay, very good. I have scrolled now. Yes, it is. For loop means it is calling n power n, big O of n power n. But basically, if you see permutation, we say n factorial, right? N factorial is nothing but big O of n power n. We write it as big O upper bound. We never write big O of n factorial. We never write this one, right? We write big O of n power n. So n factorial is written as big O of n power n. So this is one of the function, recursive function, which is taking n power n time. And if you literally see what is the time taken is, how many times it executes, it's n factorial time it executes, right? Each permutation, it will find out how many permutations are there, n factorial, 3 factorial permutations are there. So it takes n factorial time. But when we represent the time, we don't say n factorial. We don't use the term n factorial. We use n power n. We take the upper bound of that one, bigger bound. Okay. For n factorial, we write n power n. Yes, very good. You have answered, most of you have answered. Now I have two more things to explain. Now, backtracking. See, you have understood what is recursion. Okay, recursion means a function calling itself. A function calling itself. You have understood this one. Then you have understood brute force. Brute force means finding all possibilities. That can be easily done using recursion. So brute force need not always use recursion, but it is done using recursion mostly. Okay, so recursion is separate, brute force is separate. Now comes to backtracking. Backtracking is separate thing again. Okay, backtracking is separate thing. So backtracking is related to brute force once again. It's related to brute force. What does it mean? I have an example to explain this one. So even this similar example is there in my video lectures also. So I'll just repeat it quickly because I am explaining what is backtracking. You know recursion now, brute force also now. See, there are 4 seats and you have 4 people, 2 boys and 2 girls. You want to arrange them in these 4 seats, right? In a bench or in a seat, you want to arrange them, right? Now, you have to impose one condition. So arrange them. So you can arrange them in various ways. B1, B2, G1, G2. Okay. Then B1, B2, G2, G1. Then B1. Now this we have tried. G1, G2 we have tried. Now we should take this one, right? So this is nothing but permutations. So these permutations, you can get them in the form of a tree. Yes. First select B1. Okay. Okay, B1, then select B2, then select G1, then select G2, then select G2 here, then select G1 here. Okay, G1 here. Then go back. Instead of this, take G1, then take B1, then take G2, then girl 2, then boy 1, right? Then go back. B2 and girl 1 is over, right? Then one more comes out from here. Okay, one more comes out. That is girl 2 is sitting first, then boy 1, then girl 2. The next is girl 2, then boy 1. Right? So now I should go back and expand from here, right? So actually this will become a very big tree. Now, if you see this we have seen one portion of it. This is boy 1 was sitting, right? Boy 2, boy 3, girl 1, girl 2. Sorry, boy 1, boy 2, girl 1, girl 2. Then boy 1, boy 2, girl 2, girl 1, boy 1, girl 1, boy 1, girl 2. Like this, I am getting some of them. Now I should try all. So total how many it will be? 4 factorial, right? So so many permutations you can draw rest of them. So this is nothing but permutation only. Okay, so this is brute force. You can say it's a brute force. But what is backtracking? If I say that girls should not sit together, this is the condition. Condition. Okay, there is no reason. Don't ask the reason why girls should not sit together. Okay, there is no special reason for it. Just I'm imposing one condition. Okay, girls should not sit together. That's it. One of the condition. Okay. Now you can say boys also. Okay. So if girls are not sitting together, this is the condition. Now you have this condition means you cannot take all permutation. Some of the permutation will be skipped. So those permutation will be dropped, or we say killed also. The term we use killed also. Okay. So permutations will be killed. Okay. Now, when you have this condition, which is limiting some permutation, so such a condition is called as bounding function. Bounding function. So in backtracking, we try to solve a problem by applying brute force, by penetrating and getting all possibilities, but removing some possibilities by applying bounding function. This is backtracking. Have you understood this one? Backtracking is similar to brute force. Now I should say that backtracking uses brute force. So also uses recursion. But what is backtracking? Backtracking means finding all possible solutions by brute forcing possible solutions, right? And how a solution is defined by using bounding function, right? This bounding function we check if we apply this for reducing those which are not the solutions, all right? So let me see how this bounding function will help us solve this problem quickly. Sorry. Boy 1, boy 2, girl 1, till here okay. Girl 2, oh no, not allowed. Boy 1, boy 2, girl 2, girl 1, no, not allowed. Boy 1, girl 1, yeah. Boy 1, boy 2, girl 2, yes, perfect. Boy 1, girl 1, girl 2, no, not allowed. Here itself will stop, will not go further. That's how we will avoid this expansion of the tree. We don't penetrate further because here itself we have stopped. So in this bounding, by applying this bounding function, we remove some of the situations which are not related to the result. Okay, so a problem, oh, okay, let me tell you backtracking now. A problem in which you want all possible solutions, then you perform backtracking. Then you use backtracking. There are multiple solutions for a problem. You want all possible solutions. Okay, then we say it's a backtrack. And backtracking will have some bounding function. Now, if you see here, boy 1, girl 2. Boy 1 is okay. This is also okay. Correct. Boy 1, girl 2. Girl 2. No, we'll stop here. So our work will be reduced by applying the bounding function. Okay. So this is similar to brute force only, but it will have some bounding function. Then we say we use the term that is backtracking. Why the term backtracking is used here? Because it is using brute force only, right? And brute force is using recursion. So in the recursion, we do what? Backtrack only. A returning phase is there in the recursion, right? Returning phase. So that returning phase gives the sense of backtracking. Okay. Go further and further and further and further. No, wrong. This is not a result. Go back. Okay, from here, follow. No, wrong. Go back and follow. Yes, follow. Here. Yes, we got the answer. Then go back. Next path. No, wrong. Go back. From here. No, this is also wrong. Go back. Go follow the next path. Yeah, this is correct. So this is how we get the solutions. Okay. Then go back and further. Yes, this is the solution. So we got two solutions like this. So wherever the bounding function is failed, we stop and go back and backtrack and continue, So that's how this is backtrack. Okay. Now the last thing. Now listen this very carefully. I never found a clear picture of this one, right? Maybe in my lectures also, yeah, I have given the picture, but I have not mixed all the topic. Now you have started listening from the recursion onwards. Now you can get a very clear picture of dynamic programming. Listen very carefully. What is actually dynamic programming? Listen. See. If we take one problem, okay? For a problem, we give solution. Like in the beginning, I said that for any problem, the solution may be given in the form of recursive function. Yes, okay. So problem means some task, okay. For one problem, there may be multiple solutions. Solution 1, solution 2, solution 3, solution 4. Many solutions are there for some problem. Yes, you pick up any problem from daily life, okay? Pick up any problem, you ask the people, he will give one solution, other person will give. Many solutions are there for one problem, right? So you can take this one or this one. Now, when you have multiple solutions, all solutions you will not take. Now you say that, no, I have this condition. So you'll have some condition. Once you impose that condition, all solutions are not useful for you. Maybe just 2 solutions out of it are useful. So such solutions are called as feasible solution. I'm going abstract. Just follow this. Okay. Feasible solution. All right. Understood this one? Now let me put a problem. Now I say that I want to travel from one city to another city. Let us say I want to travel from Jeddah, right? Jeddah to Riyadh. I want to travel. Okay. Jeddah to Riyadh. Now, this is my problem. Now, somebody say, go by walk. Somebody say, keep on asking lift and reach there. Somebody will say, take a flight. Somebody will say, take a taxi. Somebody will say, take a, okay, what is that? A bus, take a bus, right? And somebody will say, take a chartered plane and go there. There are many solutions. Wait. Don't give so many solutions. I have only 500 riyals. Oh, condition is imposed. Now you cannot take chartered plane. You cannot take a flight. Maybe I don't know the pricing. Just say pricing of the flight. Price of a flight is 1,000 riyals. Suppose, for example. Okay. I'll reduce the price. Okay. 50 riyals. I have 50 riyals only. Okay. Now, only option left is what? You can take a bus. Or you can take a sharing taxi. Okay. 2 options are there. Got it now? Now, these 2 solutions are called as feasible solutions. So for a problem, there may be multiple solutions, but those solutions which are satisfying the condition defined by you in the problem. Okay, in the problem. This is the condition given in the problem itself. So this is called as constraint. This is called as constraint. If there is any constraint, then that constraint, whichever solution is following, we call that as feasible solution. Feasible solution. Got it? Now, if taxi takes, sorry, what was that? Yeah, bus. If bus takes 40 riyals and sharing taxi takes 40 riyals and bus takes 30 riyals, suppose. Okay. Now, 2 solutions are there. Now, this is my constraint. Constraint is I want to go in only 50 riyals, 50 bucks, but right, there are 2 solutions remaining. Now, from this, which is a minimum solution? This is the minimum solution. I want that solution actually. So why not this one? No, my objective was I want to travel from Jeddah to Riyadh. I have only 50 bucks. And what is the minimum cost? This is the actual problem. What is the minimum cost? Right? Can you give me a solution with a minimum cost? So now the point is, if there is any problem which is having one constraint and some objective of minimization or maximization also sometimes. Here in this, we have minimization. So if any problem is having an objective of getting a minimum result or maximum result, then this minimum solution or maybe some maximum solution is called as optimal solution. Optimal solution. That's it. All right, we are almost there. This is an optimal solution. Got it? Now, once again, I'm repeating. The problem is there and the problem is having constraint. And also the problem is having objective. Objective. What is the objective? Either minimum or maximum. The problem demands either minimum result or maximum result. In our example, it demands minimum result. So it means problem demands optimal solution. So if any problem is demanding an optimal solution, then we call it as optimization problem. We call it as optimization problem. Okay. We call it as optimization problem. That optimization may be either minimization or maybe maximization. We call that as optimization problem. Okay, till here is everything correct. Or is it that there is some condition and we say, well, okay, yeah. No, wait. This condition is different. Leave that, everything, leave everything. Just, this is a fresh topic. This is a fresh topic. Okay, dynamic programming. Just we are learning back. Dynamic programming. Don't mix up with the previous topic. Just forget all that. I will recall wherever required. Okay, problems are called as optimization problem. So listen, optimization problems can be solved using various methods. One is a greedy method, second one is a dynamic programming, third one is branch and bound. These are the three different techniques for solving which problems? Which problem? Optimization problem. What is optimization problem? A problem which requires optimal solution. What is optimal solution? The solution which is giving minimum result, or in some problems, solution which is giving maximum result. For a problem, there may be multiple solutions, but that solution which is giving either minimum or maximum result, and where it is also satisfying the condition. Such a solution is called as optimal solution. If a problem requires optimal solution, it is called as optimization problem. So optimization problems are solved using either greedy method or dynamic programming or branch and bound. Is it clear? Now, dynamic programming is used for solving optimization problem. This is the first and foremost thing. You should know this point very clearly first. Dynamic programming means not recursion. Dynamic programming doesn't mean brute force. Dynamic programming means an approach for solving optimization problem. This is the first. Is it clear till here? Then I will take few more minutes and finish it. Just 4 or 5 minutes and I will finish it. Any questions still here? I'm talking about dynamic programming. Okay, very good, very good. Thank you. So dynamic programming is used for solving many maximization or minimization problems only. All right. Now let me go ahead further. Okay, I have this slide. Okay. I'll use this page. Now, if there is one problem, okay. Now, when you are finding maximize solution, I said that is having various solutions, Now, you tell me, if you have to go from Jeddah to Riyadh, will you find out the rate of the flight, the pricing of the flight and pricing of, you have $50 only, right? So will you try all possible and then say, no, I should go by that bus? You will try this one, or directly you ask somebody, then he will say in $50 you go by bus only. Directly people will suggest you the solution, or you should try various solution. Can I take a chartered plane? Can I take a helicopter? You should try all these things, or easily you will say that no, I should take a bus or maybe sharing taxi. This is what I can do. Okay, in that minimum amount. Okay, you will not try all possibilities, right? You will not try all possibilities. Suppose, now listen, for a problem, there are all possible solutions. You want to find out this solution also, this also, this also, this also, all these solutions. And from all these solutions, you want to take the minimum. Now you tell me, just following what people are saying, you just go by bus or blindly taking that option without exploring all options, that is better, or finding out all possible solutions, then selecting the best one. Which is better, you tell me? First one or the second one? Just following the suggestion, or finding out all possible solutions, then picking up the best solution? Which is better, first one or the second? Yes, second one. Very good, very good. Thank you. But second one is not true in all situations. Like from Jeddah to Riyadh, you will not find all possible means of transportation and their cost. You will not do it practically. You will follow greedy method. That's what greedy method is. Means for some problems, you don't find all possible solutions. You know that if you do this, you get a solution, that's all. You don't look at any other, because you know that whatever you have done, this is optimal only. Then obviously you'll get optimal solution only. So for some problem, you don't need all solutions. For some problems, you need all solutions. It depends on the problem. So for some optimization problems that can be solved using greedy method, some optimization problems can be solved using dynamic programming. This is the important point. All right. Some can be solved using greedy without finding out all possible solutions. If you're finding out all possible solution means you are trying to use DP or branch and bound. Both are similar only. Let us stick to DP. We will not talk about branch and bound. All possible solutions. Now you tell me, finding out all possible solutions, what do you call to that? Come on, come on. Is it not brute force? Yes, it is like brute force only. Right? But conditions are there that brute force will avoid other answers, but you want maximum or minimum. Acha, one more point. Optimal solutions will be, there will be only one solution, right? Not multiple solution. In backtracking, there were multiple solutions. DP is only for one solution. Now, trying out all possibilities, just like permutation or brute force, it means definitely it uses recursion or not. Yes. So that's why DP uses recursion. DP uses recursion. Now, finding out all possible solutions using recursion in the form of a tree, we don't do it like this. We make a table and fill this small values, then we get large value, we get it like this. So we fill the table and solve it. So we solve recursion in the form of a loop. That's how DP, you find all DP problems, filling table only. But that filling of a table is nothing but the filling the values of the recursive function calls only. So DP uses recursion, but DP doesn't mean recursion. DP try to find all possible solutions. So DP is just like brute force also. But DP is mainly used for solving maximum or minimum result. So if you see all DP problems, there you find either maximum or minimum result. That's all. Okay. That's all. I have finished the talk. So I have covered all the topics. If you have any questions, you can ask. Hope you have understood everything.
Thank you, sir. It was always a pleasure having you. So if anyone having a question would like to wrap up, please do put it in the Q&A section.
DP is for solving optimization problem, but DP uses recursion. Okay, that is solved using recursion. Abdullah, I'm answering you. Dynamic programming doesn't mean recursion, doesn't mean filling the table. Dynamic programming means solving optimization problems. In that optimization problem, we try all possible solutions and pick up the best solution. For trying out all possible solutions, obviously we use recursion. But we don't create a tree, but we fill the table. That I have shown you in the Fibonacci. We can directly fill the table. Any questions? Okay. You can convert backtracking function also to a loop. Yes, every recursion can be converted into a loop. Yes. But mostly when you go to backtracking, if you see the problems, they draw the tree only. Because the benefit is what? Every time when you grow the tree at one point, it will block. Bonding function, stop. So you don't have to generate a huge tree. So we prefer solving it using recursion only, on paper, using pen and paper. And when you write a program also, it will not penetrate further. It will stop at various points. So within few calls only, it will finish. So it is just like Fibonacci. When we have the data, we were discarding the calls. So similar to that, backtracking works similar. Okay, now one last point. Okay, very good question by Mo. You have asked how can we be able to solve professional problems? So this is the question from many students, like they are unable to solve the questions. Many people ask, I'm unable to solve the question. So don't get discouraged if you are unable to solve. At a student level, you have to learn. Okay, first you have to learn and learn and learn, keep on learning. So see the solutions. Don't waste your time for struggling to get the solutions. Okay, you cannot just get the solution if you don't know any one of the concept in that required in that solution. So you are not aware, do you have the thorough knowledge about thorough concepts or not? So instead of wasting time, spend some time. Okay, spend some time, try to solve it. If you are unable to do it, 1 hour, 2 hours, enough. See the solution. Once you saw the solution, now you become stronger to solve the next problem. So obviously, you should try it. If you are unable to do it, do it. If you are looking at the solution, don't get discouraged. That's a common thing. That's the only way of practicing. Okay, you try something, you are unable to get it. Okay, you are trying to give up. Don't worry. See the solution. The next problem, you may be able to solve it. All right. So this one point. Mostly what we observe is that I'm unable to do it. My friend is able to do it. So he has already crossed that stage. Your stage he has already crossed. That's why he's able to do it. It's not that he is over smart or more smarter than you. He has already crossed the stage. Okay, he has seen few solutions. Now he's able to solve this problem. You have seen, he has seen 10 solutions. The 11th one he is solving. You have seen 2 solutions and you are trying to solve third one and you are saying that I'm unable to do it. No, you also see 10 solutions. 11th one, you can solve it. Hope you got the answer. Okay, never get discouraged. If you are giving up, unable to get the answer, means don't get discouraged. It's a common thing. It's a common thing because solution is already there now. Why do you waste your time? If you have to invent something, then you can do it. But trying every problem by yourself is a good thing. Okay, try it, but don't get discouraged. That's all. We end here.
Thank you very much, sir. Do you have one more advice for the newly or the people who are interested in competitive programming? How can they relate to recursion, algorithms, and other things together?
For competitive coding, actually, there are few things that means mostly people teach it as a course or from it is not taught in academics mainly. In academics, you don't learn about competitive coding. The competitive coding came into picture because there is a lot of competition in the programmers. Like now companies have a lot of option to select the programmer. So whoever is good in programming, they are hiring them. Okay, that's how the competitive, what I believe, what I observe. Okay. But in academics, they don't focus on competitive coding. Because you are from university student, I suggest you, first point is focus on each and every subject. Take each and every subject seriously. If you are in the beginning of your course, then try to take every subject seriously. Okay. Later on, you focus on other things. So competitive coding is the fancy thing in the market right now. So actually, there are few tricks and concepts that are used for solving various problems. So in that, one of the important thing is this dynamic programming is one of them. And the data structure concept are very useful. Okay, commonly used in competitive coding. So how to use the data structure and all, there are some known tricks. So you should learn them. First, you should learn them. That's what I was telling you. See the solution, learn them. Then remembering the solution itself is a tougher task. Okay, next time try to do it by yourself. First time only, if you're trying to do it by yourself, then you get discouraged, you'll stop. You enjoy it. Look at the solution and solve it. Look at the solution and solve it. Try to solve as many problems as you want. Then once you are feeding up in your mind and you remember them and you start using them at one stage. All right. So from the first problem, you cannot solve it by yourself. So this is the way. So make your data structure concept more clear and stronger. Because one thing, this is sure, means when you are coming out of academics, programming, you should know programming. And if you know programming, you already should know, you should also know data structure also. Without data structure, there is no programming. Without data structure, there is no programming. Every programming language is having its own data structure. We have to use them. So if you have to worry about the efficiency of programs also, so you should have the knowledge of data structure subject also, so that you can understand how to use this data structure in a particular language. Like in Java, you have collection framework. So you can understand that collection framework if you have the good understanding of data structure subject. Subject you should know. So programming and data structure goes hand in hand. All right. Then above that comes competitive coding. That are some tricks. Use how to use the data structure and solve some algorithm problem. So you can learn them. The more and more problems you can keep on learning, you have to spend time on it. Okay, that's what I can say.
Thank you very much, sir. It's always has been a very great pleasure to have you here between us and with us. Definitely would love to see you in person in Saudi one day, inshallah. It's always been a dream come true to get advice from Mr. Mohammed Abdul Bari and to watch the YouTube videos and now in Zoom. And this is always a pleasure. It's always been the legend, if I may call you, the legend of CS. Thank you very much, sir. It's been a pleasure. We don't want to take more of your time. Thank you for coming and accepting our invitation. And hopefully, inshallah, we'll see you very soon. Thank you and take care, sir.
Inshallah.